Welcome dear students, we are on the CEC Gurukul lecture and we are in the series of the electronic circuit and we are discussing the resonators. In the previous lecture we have discussed the various electromagnetic resonators. In that continuation of that lecture we will discuss the other type of electromagnetic resonator. So, in which we discuss first the surface acoustic wave, that is SAW resonator. This SAW resonator use acoustic waves that propagate on the surface of material, and they are used in the filter and oscillators, particularly in the communication gadgets, because they work at high frequency. Basically we are using a resonator, so we require the frequency. So at the high frequency we use a SAW resonator, and these are commonly employed in the mobile phones and other communication devices, and to select the certain frequency out of the large number of gain. So we can say this is the SAW type of resonator, SAW filter. You see on the screen that we are having the various surfaces on which we are having a high frequency signal we are getting, and you see on in between that we have a SAW like structure, and we are right hand side we have a reflector, internal digital transducers we are using, and piezoelectric substrate. These resonator we prepared on the piezoelectric substrate. So these are commonly employed in the mobile phones and other communication devices, and select a certain frequency out of the large number of the signals. So surface acoustic wave, that is SAW resonators, is a type of resonator that uses the surface acoustic waves to generate a resonance similar to the crystal oscillator, and it can be represented by equivalent circuit that includes an inductor, capacitor and the resistor. So this circuit model is used to understand and analyze the behavior of the SAW resonator in the various application. What is the operating principle behind it? SAW resonator use the piezoelectric effect, as you have seen in the diagram that we are using the piezoelectric substrate. So these resonator use the piezoelectric effect to convert the electrical energy into the mechanical waves and vice versa, and they are typically fabricated on the piezoelectric substrates like quartz or lithium niobate with interdigital transducers, that is IDTs, on the surface. When an AC voltage is applied, the IDTs generates the surface acoustic wave that propagates across the substance. That we have seen in here, that they generate the waves and that propagates through the surface. That is why it is a surface acoustic resonator, and these waves are then reflected by the grating reflectors, creating a standing wave pattern and resonating at a specific frequency. So if we define the design consideration of these type of resonator, so that involves carefully selecting the piezoelectric substrate material. Another is IDT geometry, and then the reflector grating spacing to achieve the desired resonant frequency. So these three things we require: piezoelectric substrate material, second is the IDT geometry, and third is the reflector grating spacing to achieve the desired resonant frequency and other performance characteristics. The equivalent circuit model can be used to optimize design parameters for the specific applications. So the SAW resonators are used in various applications, that is the oscillators, filters. In the oscillators, use a frequency reference in the electronic devices. As a filter, use the specific frequency in the radio or the communication system. So if you select it. Another is the delay lines, used to delay signals for the various applications. Then for the sensing, used to measure the temperature, humidity, strain, as well as the detection of the gases and liquids by using this SAW resonator. and its behavior can be modeled using an equivalent circuit, which often includes the following component. Number 1 is the static capacitance, that is C0. C0 represent the capacitive coupling between the IDTs. Another is the motional inductance, that is LS, represent the dynamic inductance associated with the wave propagation. Another is the motional capacitance, that is the CS, that represent the dynamic capacitance associated with the wave propagation. Then radiation resistance represent the power dissipation due to the wave radiation. Then we use the motional resistance, that is represented by the RQ, and that represent the energy dissipation due to the wave scattering. So these are the various components which can use for the resonator, that is the SA resonator. Another type of resonator is the piezoelectric resonator. Piezoelectric resonator are a type of resonator commonly used in the electronics due to their small size, high stability and excellent frequency control, and they utilizes the piezoelectric effect, which refers to the ability of certain materials to generate an electric field when subjected to mechanical stress and vice versa. So the core component of piezoelectric resonator is a piezoelectric crystal or the material such as quartz or ceramic, which exhibits the piezoelectric effect. When the electric signals of the resonant frequency is applied to the crystal, it undergoes a mechanical deformation. As it is a piezoelectric material, so whenever we apply the electric signal to the resonant frequency at the crystal, so it undergoes the mechanical deformation, which causing the crystal to vibrate at a desired frequency, and this vibration generates the mechanical waves that propagation through the crystal that create the resonant effect. So the vibrations generates mechanical waves that propagate through the crystal, creating the resonant effect. So piezoelectric resonators offer the several advantages over the other type of resonator. It provides the high stability and accuracy, ensuring the precise control of the frequencies. This makes them suitable for applications that require the precise timing or synchronization, such as communication system and electronic equipments. Secondly, piezoelectric resonators are compact and lightweight, so making them ideal for use for the portable devices and miniaturized circuits. Moreover, we can use for the flexible devices also. So their small size allows for easy integration into the various electronic components without compromising performance or the functionality. Furthermore, piezoelectric resonators operate over a wide range of the frequency, that may be from the few kilohertz to the several megahertz, making them versatile for different applications. They can be used in various electronic devices including oscillators, filters, sensor and transducers. You can see on the screen, this is a one type of the piezoelectric resonator. So the thickness and the height and the substrate we use according to the frequency we required, according to the resonant frequency we require. Another type of resonator is the YIG resonator. What is this YIG? Is the yttrium iron garnet resonator, and can be used to design the oscillators and the filters. So a YIG crystal has a very high Q value, so enabling oscillators to be designed with a very low phase noise, multi-octave Bandwidths are another benefit that can be achieved by using the YIG resonator. You can see this is the YIG resonator. So, material which we are using the yttrium iron garnet. So, you can see there is electromagnet and magnetic field is applied here. So, microstrip are there and the coupling loop are there. So, it is a polished YG sphere. This is the one type of YIG resonator. It is mostly used in the sphere configuration. However, other shapes have also been used over the year. So, YIG will resonate at microwave frequency when it is immersed in the direct current magnetic field. So, this resonance is directly proportional to the strength of applied magnetic field, which is generated using an electromagnet, a permanent magnet or a combination of the both. So, this resonance is directly proportional to the strength of the applied magnetic field that is generated by using the electromagnet, permanent magnet or the combination of both. A number of YIG based products are offered by Microlamba Wireless, and this type of where we are having a which cover the range of 500 megahertz to the 44 gigahertz. The output power that range from the 0 to plus 23 dBm, and that company also offer a line of YIG tuned filters that span from 500 megahertz to the 50 gigahertz. Another type of the important resonator is the MEMS resonator. MEMS, it is very miniaturized devices. We can say that MEMS resonator are miniaturized resonators and they are used in semiconductor technology with features on the micron scale. Due to their small size and the power consumption, they are applied to use such as sensing and portability applications. So, MEMS, that is a micro electromechanical system resonators, are the tiny mechanical structures that vibrate at specific frequencies that often used for the application like oscillators, sensors and the filters. They work by converting electrical signal into the mechanical vibrations and vice versa, usually using piezoelectric transducers mechanism. So, what are the advantages of MEMS resonator? They are small in size as it is a miniaturized device that is also prepared on the nanoscale, and they are used in the flexible electronic devices. So, MEMS resonators are very small, allowing for the miniaturization of the devices. Another is a high frequency. MEMS resonators can operate at a high frequency, making them suitable for the various application. Low power consumption. So, MEMS resonators can be designed for the low power consumption, making them energy efficient. Moreover, high reliability. MEMS resonators are generally highly reliable due to their simple design and small size. So, one of the flexible MEMS resonator you can see on the screen, and these operate based on the mechanical flexing and are employed in the precision sensing. You see both the side we have substrate, we have ground plate, then acoustic guide wave IDT. So, the MEMS resonator to generate a precise timing signal often used in the clocks and timing circuit. Moreover, the MEMS sensors, MEMS resonators to sense changes in the physical parameters like mass, acceleration and temperature. MEMS filter, these use the resonant properties of MEMS resonator to filter out specific frequency range. What are the key component and operations of the we can say is the MEMS resonator, that it is a input transducers, and this component converts the electrical input signals into the mechanical force such as electrostatic force. Another is a mechanical resonant structure. This structure vibrates at the specific frequencies determined by its physical properties like mass, stiffness and the dimension. Output transducers, this component senses the motion of the resonant structure and converts it back into the electrical signal. So, what is the working principle behind the MEMS sensors, MEMS resonator? First, we use the electrical input. So, an input electrical signals, typically a varying voltage is applied to the input transducers. Another point is the mechanical excitation. The input transducers uses the electrical signal to create a mechanical forces that excites the resonant structure. Then resonance, the resonant structure vibrates at its natural resonant frequency determined by its physical property. The fourth one is the output signal. The output transducer senses the motion of vibrating structure and converts it back into a electrical signal. So, another important consideration is below are the guidelines that can be used in the construction and implementation of the resonator in the different environment and with the other circuit components. These are used in the environmental stability. So, resonator have to be made to ensure different environmental factors such as temperature variation, humidity, mechanical vibration to avoid the fluctuations in the performance. So, these are the type of the MEMS resonator. Now, we discuss the dielectric resonator. A dielectric resonator is a piece of dielectric, or we can say it is a non-conductive but polarizable material. Basically, we use the ceramic that is designed to function as a resonator for radio waves. Generally in the microwave and the millimeter wave bands, but here we take the dielectrics in the radio wave. So, the microwaves are confined inside the resonator material by the abrupt changes in the permittivity at the surfaces and bounce back and forth between the sides. So, at a certain frequencies, the resonant frequency, the microwave from standing waves in the resonator oscillating with large amplitudes. So, dielectric resonators generally consist of a puck of the ceramic that has a large dielectric constant and having a low dissipation factor. So, the resonant frequency is determined by overall physical dimensions of the resonator and the dielectric constant of the material. So, the resonant frequency is determined by overall physical dimensions of a resonator and the dielectric constant of the material. So, dielectric resonator functions similar to the cavity resonator. Hollow metal boxes that are also widely used as a resonator at microwave frequency, except that of the radio waves are reflected by the large changes in the permittivity rather than by the conductivity of the material. So, these metal surfaces become lossy reflectors. So, dielectric resonators are used at these frequency, at millimeter wave frequency we use it. So, dielectric resonators main use is in the millimeter wave electronic oscillators, and these are the dielectric resonator oscillator DRO. To control the frequency of the ratio wave generated, they use also the band pass filter as well as the antennas. These resonator displays the many similarities to the resonant metal cavity. So, there is a one important difference between the two. While the electric and magnetic field are 0 outside the wall of the metal cavity, that is, open circuit boundary conditions are fully satisfied. So, these fields are not 0 outside the dielectric walls of the resonator. that is the open circuit boundary conditions are approximately satisfied. Even so, electric and magnetic field decay from their maximum value considerably when they are away from the resonator wall. So, most of the energy is stored in the resonator at a given resonant frequency for a sufficiently high dielectric constant. So, dielectric resonators can exhibit an extremely high Q factor that is comparable to the metal walled cavity. So, you see on the screen that what type of dielectric resonator that can be mounted in the waveguide to serve as a microwave filter. So, you are seeing the dielectric type of resonators are there. This is a dielectric band pass filter consisting of the 3 dielectric resonators mounted in the transverse direction. You can see on the screen that it is a transverse direction where the 3 dielectric resonators are mounted, and it is work as a filter. So, there are the three types of the resonant modes that can be excited in the dielectric resonator. First is a transverse electric, second is a transverse magnetic, and third is hybrid electromagnetic mode, TETM and HEM mode. So, theoretically there is an infinite number of the modes in each of the 3 groups, and desired mode is usually selected based on the application requirements. So, generally mode is used in most non-radiating applications, but other modes can have the certain advantages for the specific applications. Like they are the most so since dielectric resonator is usually enclosed in the conducting cavity for the most applications, the real resonator frequency are different from the one calculating above. So, as conducting wall of the enclosing cavity approaches the resonator, changes the boundary condition and the field containment start to affect the resonant frequency. So, the size and the type of the material encapsulating the cavity can drastically impact the performance of the resonant circuit. So, this phenomena can be explained using the cavity perturbation theory. If the resonator is enclosed in a metallic cavity, so resonant frequency change in various form. Number 1, if the stored energy of the displaced field is mostly electrical, its resonant frequency will decrease. If it is mostly magnetic, then its frequency will increase. So, this happens to be the case for the mode. Most common problem exhibited by the dielectric resonator circuits in their sensitivity to the temperature variation and the mechanical vibrations. Even though recent improvements in the material science and the manufacturing mitigated some of these issues, compensating techniques still may be required to stabilize the circuit performance over the temperature and the frequency. Another type of the resonator is the quartz crystal resonator. So, quartz crystal resonator use the piezoelectric effect of the quartz, as quartz is a piezoelectric material. So, it just use the piezo electric effect. So, and it applied mechanical force to the certain dielectrics to cause the relative displacement of the positive and negative changes centers inside them, resulting the polarization. So, appearance of bound charges with opposite sign on the surface of the both the ends of the medium within a certain stress range, the mechanical force and the charge have a linear and reversible relationship. So, the resonant component is made, you can see on the screen, this is the type of resonant circuit. So, working principle, and in which a crystal refers to a solid in which the atoms, molecules and extend in all the direction in a regular and repetitive pattern. So it is almost all elastic materials have a natural resonance frequency which can be used through the appropriate sensor. So for example, steel has a good elasticity and a fast speed of the sound. Before quartz crystal are widely used, steel are used as a mechanical filter. So these are the various type of quartz crystal, and these references we have used for the preparation of the slide, and thank you very much.